What's up, mathematicians? Justin here, and in this video we'll be talking about area. Okay, so before we get into area, let's talk about one-dimensional measurement. If something is one-dimensional and you're measuring it, what you're doing is you're measuring its length. And how do you measure the length of something? Well, you use a measuring tape. How long is this table, for example? About 41.5 inches. So simple enough, right? Just take your measure. If your measuring tape isn't long enough, you can just measure bits and pieces and add them all together at the end. Simple, right? But what if something is so big or inaccessible? What if you have to measure something that you can't measure directly? Right? So that's where trigonometry comes in. We use trigonometry to measure things that we can't measure directly, or to sort of plan out measurements when we're creating drawings and such. So for example, with the tree the tree that we looked at in several videos, I didn't have the ability to go to the top of the tree, so I used trigonometry to measure the height of the tree. Okay, so that's one-dimensional measurement. Length. Use a tape measure if you can, otherwise trigonometry. Now let's think about two dimensions. So our two-dimensional unit of measurement is the square unit. If you're measuring in meters, it's square meters. Measuring in miles, it's square miles, etc. So when we're looking at our dot grid paper, so area is based on, and I encourage you to take notes as always as well. So area is based, let me actually write that whole thing out. So this concept of area, the fundamental unit is a square. So area is based on the square unit. Okay, so using this dot grid paper, I can easily make a square unit. So unless otherwise specified, my unit is the distance between two dots on this paper. So I draw a line from one dot to the next. That is my distance unit when I'm using this paper. But now, in order to describe two dimensions, area, I'm going to have to draw a little square connecting four dots. So there it is. That's my square unit. Okay, now let's think about one of the easier shapes, probably the easiest shape to find the area of, and that is a rectangle. All right, so we got a rectangle, and let me go ahead and draw one out here, and I'll go ahead and draw it 3 units high and 4 units long. Okay, so what is the area of this rectangle? Well, you probably already know that the area of a rectangle is found by multiplying the base times the height. Here, the base is 4 and the height is 3. And so we get that the area is 4 times 3, which equals 12. Now this is easy to verify because I can just go ahead and draw in all of these square units, and I can count them up. All right, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sure enough, 12 square units in that rectangle. This formula of multiplying the base times the height works. So we get that the area of a rectangle is equal to the base times the height. Something you probably have known for quite a while now. Okay. But what about a triangle? Let's do triangle next. Okay, so triangle. Let's go ahead and draw in a triangle. And I just want to make sure I'm counting this out correctly. I'm going to go ahead and draw it out nicely with my straight edge here. Now, you probably already know the area, the formula for the area of a triangle. That's okay. I still want to go through one method that we could find it. So we have this distance along the bottom. We call this the base. And then we have the height of the triangle, which does not necessarily go along one of the sides of the triangle. It would only do that if it were a right triangle. Most triangles are not right triangles. And so your height is going to be an altitude that is perpendicular to the base. Goes from the point opposite the base to a point on the base such that it is perpendicular to the base. Okay, so you probably already know this formula, but let's go ahead and see how one might figure it out if you don't know it. This may have been the method that some ancient societies used to determine the area of a triangle. So imagine you take this top part of the triangle. What I did here is I just drew a line halfway up the altitude, right? And now I'm just going to imagine reflecting the top part of the triangle over this line. Well, because I drew it halfway at a right angle, this point will get reflected right down to here. And so I'll end up with that line there, and this side will be reflected down here. And so I'll end up, and by the way, an interesting activity would be to, get a piece of paper and maybe a scissors and actually do this hands-on. But anyway, I now have my triangle folded over. Now these two triangles here that you see, they have, imagine them as a piece of paper. There's two layers there. So let's go ahead and cut this off, sort of imagine cutting it off and attaching it to this side. Well, if we did that, it would come to fall on that triangle right there. This triangle here would go right there, and then this smaller triangle here would fill in this space right here. Okay, so that's kind of cool. The overlap space, neatly falls into this area and that area right there. So if this is the height, and I drew this line halfway up, that means this is 1/2 the height, right? Well, now I've taken the original triangle, I have folded over the top and then cut those two pieces off such that they lay right here and make up a rectangle that's half the height of the triangle I started with. Well, because I know the area of a rectangle is just base times height, now I know the area of the original triangle is the base times half the height of the original triangle. And that's where we get this formula that the area is 1/2 base times height. Okay, still simple enough, right? The ancient Egyptians and other societies as well, they had formulas for the area of a rectangle, area of a triangle, and they were able to calculate these things. Let's move on though to the area of a quadrilateral. And when I say quadrilateral, I mean a general quadrilateral, not necessarily a rectangle. Let's go ahead and draw one of these on the paper. And so let's see. I'll just draw out some points here, here, and there. That should work. Okay. I'm just going to go ahead and connect these dots. Okay, so this is a much more challenging shape to find a formula for. If you want to find the area of this shape, the formula is much more challenging. There are a few different things you could do, right? One is to actually look at the grid and draw it out, and you can count all these unit squares inside it, and then the ones that are sort of half in and half out, maybe you can count those as halves. This is an activity that you may have done in elementary school at some point to approximate the area of a so-called irregular shape. But the quadrilateral is still pretty regular, so we would like to be able to find the area of this shape. Well, it turns out the Egyptians had a formula to find the area of this shape. And in order to use that formula, let's go ahead and label these sides. So I'll label it on the outside. So we'll call this side A, this side B, this side C, and this side D. And so these variables will represent the lengths of the corresponding sides. So the Egyptian formula was as follows. They said that the area of this quadrilateral would be 1/2 times, oops, let me write that as lowercase a, 1/2 a plus c times 1/2 b plus d. Okay, so that's what they said the area was. Interesting little formula. And I would actually challenge you to pause the video and try this formula out. You'll have to actually measure these out. So on your paper, you can measure them out, calculate out, and see if you can figure out if this formula is correct. Play around with it for a little bit, and you might discover something that's somewhat interesting. Go ahead and pause the video and do that if you have the time. Okay, so I'm going to go ahead and measure the lengths of these sides here. And I'm doing centimeters here. So, all right, so this is 7.5. This one here is, can't quite see, the document camera's in the way. I'm going to go 4.6 for that one. And that looks like 3.4. And finally, this side right here. That looks like 3.8 to me. All right, so 3.8. This is all in centimeters, but I'll just call those my units. Okay, so let's use the Egyptian formula. So the area of this shape is 1/2 times, let's see, 3.8 plus 3.4 is 7.2 times 1/2 of 4.6 plus 7.5, 4.6 plus 7.5, 12.1. All right, so let's go ahead and plug that all in the calculator. Here, I'll go ahead and do it here so you can see what I'm doing. So 7.2 times 12.1 times 0.5 times 0.5. And we get an area, a total area of 21.78. Okay, so we use this formula, we got this area. How do we know if it's right? Is there another way we could find the area of this quadrilateral? Well, wait a second. We do know how to find the area of a triangle, right? So let's just divide this into two triangles. Okay, and now I'm going to, let's see if I can do this. I gotta try to find the altitudes of these two triangles. I'm just going to use this as my right angle, and there will be one of my altitudes. And then my other altitude, again, use this as a right angle, sort of a square. Other altitude is right there. Now I need to find the lengths of these altitudes. And also need to find the length of this side. So this might end up getting a little messy. I apologize here. Okay, so this distance right here, that looks awfully close to 7, right on the money. So we'll say that's 7. Okay. Now, this distance here, looks to me like 1.9. Might even be slightly under, but 1.9 I think is the closest. 1.9. And now this distance here, that is 3.7 is the closest, so 3.7. So the 3.8 is this one on the outside, and 3.7 is this altitude. Okay. And here's the other altitude, 1.9. Okay. Now we can use that information to find the area of these two triangles. So the first triangle is going to be 1/2 times the base, which is 7, times the height, which is 3.7. Okay, so that's this triangle right here. Let's plug that in our calculator. So 0.5 times 7 times 3.7, 12.95. All right, now let's find the area of this triangle up here, and that's going to be 1/2 times 7, again is the base, times 1.9. All right, let's see what happens. 0.5 times 7 times 1.9, 6.65. Ooh, and look at this. Instead of using my calculator, let's add this up the old-fashioned way because it's so nicely lined up. We got 0 here, carry the 1, 6, carry the 1, my decimal point is there. 3 plus that gives me 9, and bring down the 1, and I have 19.6. Now this is interesting, right? I get 19.6 as the area of this quadrilateral. But if we look at the the area that we get from the formula from the ancient Egyptians. Now, by the way, this is not from the modern Egyptians. I'm sure modern Egyptians know how to find the area of a quadrilateral, but this ancient formula gives us something that is not too far away, but significantly different, right? This 21, if you round to the nearest tenth, 21.8 versus 19.6. Let's think about this for a second. So why did the Egyptians, develop formulas for finding the areas of quadrilaterals? One reason they did it is to charge the farmers taxes, right? So it's like, okay, you as a farmer, you have this much land, and based on the amount of land you have, you owe us this much tax. So they would charge based on the amount of land. So if the tax collector showed up with their formula and measured everything and said, okay, so you have 21.8 square whatever units of land. So let's say it's one silver coin per square unit. All right, so you owe us, let's round to 22 silver coins. Well, you might say, wait a second, or maybe I should say 10 silver coins, because that'll come out better. So if it's 10 silver coins per square unit of land, that would mean 218 silver coins if this was the area of your land. But if this was the area of your land, we'll multiply that by 10, and it's 196 silver coins. Well, hang on a second. You know, okay, first of all, we can see that the Egyptian formula is wrong. And there are other more extreme cases. If you made this really thin, you know, or let's say you made, I'll put it right here. So let's say you made a parallelogram type thing like this that was really thin, okay? This would come out to an area that was that would be significantly off. The closer that the area is, the shape is to a rectangle, the closer this formula is to the correct answer. But the thinner it is, the more sort of askew it is, the more it's going to be off. So, you know, this makes me wonder, wait a second. Did these ancient Egyptian mathematicians, tax collectors, whoever they were they just dumb? Or were they swindlers? Did they go up to these farmers and be like, okay, you owe us 218 pieces of silver? And I mean, is the farmer going to have these formulas and measurement techniques? Probably not. They'll be like, all right, pay up. But turns out that farmer should have only been paying 196 silver pieces. So yeah, I think this is an interesting situation, right? Is it true that, you know, it is true that the Egyptian formula was incorrect. Now, I have a hard time believing that the society, the ancient society that built the pyramids, that did calculations so precisely that, you know, these pyramids are amazing and symmetric and really perfectly shaped, you know, feats of construction. I have a hard time believing a society capable of that would be, you know, would not be aware that this formula was incorrect. So, you know, maybe they were just like, yeah, it's wrong, but you know what? Who's going to know? Those farmers don't know anything. So maybe this is another reason to learn your math. Make sure you're not getting cheated by the government. Just a thought. Okay, so it turns out there is a precise formula for the area of a quadrilateral, but it's a little bit involved. So if you have a quadrilateral like this here with sides A, B, C, and D, you also need to, you know, specify two angles. So we'll call those alpha and beta. They would have to be across from each other. And in this case, we can say that the area of this quadrilateral is 1/2 A times D times the sine of alpha and plus 1/2 C times B times the sine of beta. So there is the area, the formula, the general formula for the area of a quadrilateral like this, an irregular quadrilateral. So, you know, it's a little bit tricky. Maybe we can't fully blame the ancient Egyptians for not getting it quite right. But I think that if they had worked harder, they could have, you know, used a technique like this, splitting the triangles, and gotten, figured out a way to measure it a little bit more accurately. So this is an interesting situation because it means that maybe we have to take a more careful look at some of these things we're doing. If, for example, the ancient Egyptians used a formula like this, whether you know, an incorrect formula, whether they knew or didn't know is incorrect, they used it, and how do we know the formulas we're using are correct? And how do we know some of these other things we're assuming are correct? These are questions that we're going to have to start investigating in a little bit more detail. So anyway, just to wrap up, quick reminder, okay, this lesson is about area. Started mentioning like, oh hey, length, use a tape measure, or trigonometry if you can't measure directly. Area is based on square units, and areas for rectangles, triangles, quadrilaterals, and other shapes as well turn out like, basically we end up using formulas which will convert, you know, whatever measurements into the number of square units. So like these are all being converted into their equivalent in square units. That's what these formulas do. They convert the dimensions into the equivalent of square units. So it's all based on square units still. And, you know, What happens when we go past area? Of course, volume. We can measure three-dimensional space. We're not going to do that at this point in this unit. I know it is a type of measurement, but it's just not something we're going to cover right now. So what is it? Distance, area, and volume. And those are the three big ones, right? Wait a second. There is another type of measurement that we do all the time in geometry that I haven't mentioned yet. Can you think of it? I'll tell you in the next video, and I hope to see you there. Bye-bye.